I'm recording now.
Okay, if you come up with one in particular, let me know. Otherwise, let's just do this one. So let's do the integral from e to e squared of 1 over x natural log x dx. Okay, so right off the bat, do we have an antiderivative of this in mind? I don't. It's kind of complicated, so maybe we can use U-substitution. So we have a couple choices, right? We have an x and a natural log of x in the bottom. We can choose to make one of those our derivative, our u. So typically what we want to do is see if one of these things has a derivative that's present in the other part of this. And you can see that by rewriting this slightly. Or you can just try both, but you can rewrite this slightly and say, instead of 1 over x times natural log x, we can separate that as 1 over x times 1 over natural log of x. And now we can see that if we choose u to be natural log of x and we find du, well, the derivative of natural log of x with respect to x is 1 over x dx. We have this piece here. Oops, forgot that. We have this piece here. So that means we're in good shape. Okay, let's solve for dx. So dx becomes, if we multiply x to both sides, we get x du. And now let's plug in u and dx. So again, we don't know our limits yet. We didn't find them yet. But we know that we have, instead of 1 over natural log of x, we said natural log of x was u. So we got 1 over u. And instead of dx, we have x du. Those x's cancel out, hooray. And if we simplify this a little bit, we again don't know our limits yet, but we have 1 over u du. All right, it's at this point we should pause and ask, did U-substitution go as planned? So do we have any x's here? We do not. We were able to get rid of them all. We just have u's. That means we are on the right track. We've found a good U-substitution to use. I want to pause here. Any questions on this? So we haven't found these limits of integration yet. That's okay. That's what's coming next. Great. Okay, so like we said, U-substitution went well, but our original limits of integration here were x values. We want u values, so we don't have to substitute back in later. Yes, Alfonso.
I was watching a video yesterday, and you know, integrals is basically like finding the space within a shape, right? Are we gonna, I don't know if we're gonna get to this test, but are we gonna do that while the shape is moving?
Well, the shape is moving.
Yeah. So like, I don't know, splitting into parts or something.
I'm not sure what you mean while
Are
the
you talking
shape.
about rotating around an axis?
Yeah.
Oh, not yet.
That
But
is,
it does get to that point, right?
Yes, the course does. I don't know how far we're gonna get.
there's gonna be some, I'll probably do a video on it. It'll have to be outside of class time just because, we're running so fast towards the test. But don't worry, there will be some material, like, I'll probably do a video on it.
Okay, no, actually, no, I think I'm just getting too deep.
No, it's a good question. It's a good thing to think about. That stuff is notoriously difficult, and we have limited time left together before the test. So we're gonna have to, make some decisions as to what to cover. That isn't super highly tested. If that's any reason to go over it less, I don't know, but
The physics is pretty difficult too.
yeah,
They're both difficult.
physics is not my thing. Okay, so yeah, we have this U-substitution. It worked out. We don't have the limits yet. Only 7 students in that class. Geez. Okay. So let's find our new limits of integration with x's, with u's. So we want u values. So we say when x is equal to e, u is equal to natural log of e. And the natural log of e, 1. Okay, and then we have our other limit, which was e squared. So when x is e squared, u is the natural log of e squared. And if you remember your exponent rules, we have a log with a power in it, so we can pull the power out front. So we have 2 times natural log of e, which we already found natural log of e is just 1 times 2 is 2. Okay, so we have our new limits of integration. It is from 1 to 2.
Then you can start plugging in, right? You plug in ln of x and start solving it from there. Oh no, you just plug in 2 and 1, right?
Yeah, I think you got it. Don't hesitate and backtrack. You got it. So from here, right? You said natural log of x. We need to take an antiderivative, which would be, it's almost the natural log of x. It's natural log of the absolute value of u, right? We're dealing with u, and we need those absolute value signs. We don't have plus c. I made a mistake. Because this is a definite integral, we don't need plus c. That is for indefinite integrals. Instead, we are evaluating this stuff when u is equal to 1 and u is equal to 2. Okay, so when we plug in our u values, we have the natural log of the absolute value of 2 minus the natural log of the absolute value of 1. Well, okay, the absolute value of 2 is 2. Yeah. Yeah, let's do that. So let's actually see why the c goes away. So if you forget that you don't need to deal with plus c for definite integrals, that's okay. You know why? Because it works out that the c's cancel out. So we have this general this general antiderivative, right? We have our plus c. We don't know what c is, but we know we need to evaluate our antiderivative at our limits. So when we plug in just as we would normally, our limits of integration, right? You plug the top one in and then subtract, plugging in the bottom one. Okay, so we have natural log of absolute value of 2. That's natural log of 2, right? Absolute value 2 is 2. We have plus c. Now we have to distribute this minus sign. So the absolute value of 1 is 1. So I can replace those absolute value bars with parentheses. And again, we distribute this minus sign, so we get minus c, and the c's go away. Plus c minus c equals 0. So this is why it's not a huge deal if you put in plus c, if you forget, but we don't need this.
The c's will always cancel out for every definite integral, and that's why we never put plus c for a definite integral where we have the bounds. But you can do it every single time. You can put in plus c every single time. You're just going to spend slightly more time canceling out the c's.
Yes.
Also, ln is only valid for positive x's. ln of x is only valid for positive x's. That's why we need an absolute value of x. If you try and put in a negative x, it's going to be undefined.
Yes. So I did go over this a little bit in one of my videos, but the reason, natural log of x is only defined for x greater than 0, right? It's never going to pass this y-axis here. So we need an absolute value of x in case we do have some negative values.
The reason why is it's the opposite of e of x. It's the opposite operator, and e of x can never be negative. And so when you're looking for a number that would somehow make ln of x e of x negative, you're never going to find it. So that's why it's just for the same reason that e of x can never be negative, no matter what x value you put in.
Didn't draw that very well. Okay, that's slightly better. Or you can just remember that when we take the antiderivative of 1 over u, we need natural log of absolute value of u. But there is a reason why, and this is the reason why. Okay. The last step here, the natural log of 1 is 0. Okay. We can get our final answer a few different ways, but natural log of 1 is 0, right? This is basically asking e to what power is 1, and e to the 0 is, yeah, there you go. E to the 0 is 1. So natural log and e are opposites, right? So yes. Okay, so our final answer here is the natural log of 2. And again, it's not wrong to say natural log of the absolute value of 2, but we don't need to. Absolute value of 2 is 2. Okay, so let's zoom out. Give you a chance to look this over. Is it all in frame? It's mostly in frame. Okay. Let's take a moment, look that over. In the meantime, I will look for another question unless you have one that you'd like to go over.
Just letting you know, I've shown my U-Substitution a different way. What I've done is we take the integral and then we plug x back in for u, or whatever the u value is, and then we do the bounds. And I've always stressed, hey, you have to plug back in for u after the integral, because we never changed our bounds and their bounds are still for x. So you can choose to do it Mr. C's way, where it's like, hey, we don't want to get ourselves confused, so we should change our bounds immediately. When we U-substitute, change our bounds immediately. So it's whichever way you want to do that. Up to you.
Would you like to see both ways? What if I go above and beyond and use both your methods to check if the other is right? You could do that. Don't do that on a time test, but yeah, you can do that.
Yeah, I don't think it's necessary, because the main issue is figuring out whether the integral is right. The bounds is something that's kind of secondary to that.
Do you want to see Mr. Bay's way?
I actually think your way is better than mine. I've just been showing it my way, and it's only because I haven't done it in a while that I forgot that you probably should plug in for the bounds first.
Okay, I mean, I think they both have their benefits and drawbacks, but if you've seen it already, that's okay. Yeah, let's move on.
I didn't realize you hadn't shown a definite integral for U-substitution yet, so I just assumed that, I don't know.
Yep, never came up for me. Let's do another definite. You know what? I don't like any of these problems. I want to do a different one. That's a problem. Okay. Okay, so this is from your homework. I kind of want to put, so it's an indefinite integral, but I kind of want to put limits of integration on it just so we have some practice with it. So let me think about what ones we could do. Okay, so again, I don't know an antiderivative of tangent squared secant x squared. What's the yeah, but secant squared x. What do we know about secant squared x with calculus? Okay, so 1 over cosine squared x, yeah. But with calculus, trig derivatives, it just so happens that taking the derivative back with respect to x of tangent of x is secant squared x. So this is pretty suggestive of the u we want to choose, right? we choose a u and then we take its derivative. So let's let u be tangent of x. Because we already know the derivative. Oh, that's the worst u I've ever drawn in my life. Derivative du is the derivative of tangent x with respect to x. That's secant squared x dx. Okay, so let's plug in and see what happens. Any questions so far? Derivative of tangent is secant squared. It's just one of those derivative. Okay. Let's solve for dx. We can do that by dividing both sides by secant squared x. And we get dx is du over secant squared x. So let's plug in u, plug in dx. All right, since we're plugging stuff in, we don't know what our limits of integration are yet. We know tangent is our u, but we have tangent squared, so we need u squared. And then we have secant squared x times not dx anymore, but du over secant squared x. And hooray, those secant squareds go away. We are left with u squared du. Okay, it's at this point we want to do our check. Do we have any x's left? No, we do not. We just have u's. That is a good thing. That means we did it right. And now we can find our limits of integration. So our old limits of integration were 0 and pi over 4. So we want to say when x was 0, u is tangent of 0, which is 0. So, yeah, 0. Okay. Similarly, when x was our other limit, which was pi over 4, u is tangent of pi over 4. And from our unit circle or reference table, whichever one you want to use, tangent of pi over 4 is 1. So our new limits of integration are 0 to 1. Okay. We have a power rule situation here. We need to find an antiderivative of u squared. So if it's power rule and it's anti-differentiation, we need to increase the power and divide by that number. So we have u cubed over 3, all evaluated at 1 and 0. We don't need a plus c. This is a definite integral, as we showed above. Okay. We don't need to plug in for u because we already did that. So now we just plug, sorry, let me rephrase that. We don't need to plug in tangent x back in for u because we already dealt with our limits of integration. We put them in terms of u. These are u values. Yes, so I forgot tangent's not on the unit circle. So these are u values, we just plug them in. So we have, well, plug in the top one, u cubed over 3 minus plug in the bottom one, 0 cubed over 3. That one goes away. And we're left with 1 over 3. So we started with something really gross, and we ended with a nice fraction. Isn't that satisfying? How are we feeling about?
Javi, oh, sorry.
That's okay. Go for it.
Just curious, Javi, you've seen it my way and Mr. C's. Which way do you like, just so I know for the future? Do you like making the new bounds as in terms of you?
I like yours right now,
or do you like
because I've seen it more. But I think both could be used well. I'm just used to seeing yours
okay
now.
so you okay sounds like you're comfortable either way then. Okay, I'm just curious. I feel like I should be teaching it your way, Mr. C.
We can talk about it more. Again, I think there's benefits and drawbacks to both. So there's one thing here that I really don't like about this method, but we can talk about the two of us.
Sure.
Okay, we got about 5 minutes. Any particular questions, or just rush through another one?
Inverse trig function. I'm messing with you.
I don't even know if that's. Do you have a problem ready? Because I don't.
I do not know.
Okay, I can make.
If you want me to get a problem for you, I can.
I can make it up. It's not going to be a definite integral though, because I can't make that up right now. Let's do. Hold on, anything about this. Yeah, so I got my degree in applied math.
Mine was in chemical engineering.
How come I'm blanking on a question where we could do this?
Well, if you want to use U-substitution, you could do something like 4x squared, 1 plus 4x squared. So
4x squared. Okay. I was trying to do, yeah, okay. Yeah, that's a good idea. Thank you. Let's just go with that. Okay. So this kind of resembles one of the derivatives we've seen. It's not one that we've used a lot since Mr. Bay and I have been here, so I'm not sure how comfortable you are with this one.
I showed Javi a problem like this.
Wait,
Okay.
what is it going to?
I'm just leaving him off because I can't think of appropriate limits right now, and we only have a few minutes. So this will just be an indefinite integral. Okay, but does this kind of resemble anything we've seen before? Any derivative we've seen before?
Yeah.
Yeah, which one?
This one question Hugh did on question, I think yesterday.
So yeah, this kind of looks like the inverse tangent of x. The derivative of the inverse tangent of x is 1 over 1 plus x squared. So it's not quite that, right? Maybe we could rewrite this as something squared.
Yeah, 4x squared, I think that would work. And turn it and then find the derivative. Wait.
So if we want something squared, right? This 4 is not a part of the x squared yet. So what squared gives us 4? Two. Right, so just like we would need to distribute this squared to both of these terms. So 4x squared is not the same as 4x squared. Okay. Okay, so let's let u be 2x. Then du, sorry, we have like limited time, so I'm just gonna power through. Please interrupt me if you have questions. Then du is 2 dx. So dx, we divide both of these by 2, we get du over 2. And we can plug in our u and our dx into our equation. So we have 1 over 1 plus, well, we rewrote this part, right, as the quantity of 2x squared. So now if we plug in u and dx, we have 1 over 1 plus, our u was 2x. So this is 1 plus u squared on bottom. And our dx was du over 2. So do we have any x's? No, we do not. We just have u's. That means we did it right. From this point, let's pull out the half that is from here. So we just have, let's rewrite it this way. 1 over 1 plus u squared du. And hey, that looks exactly like this, except with u's. So the integral of 1 over u squared du is just inverse tangent or arctangent of u. But we have this half out front, so we need to keep it there. And this was an indefinite integral, so we need plus c. And finally, since this is an indefinite integral and we do not want u's, we want x's, we need to plug back in for u. And our u, again, was 2x. So we have 1/2 inverse tangent of not u, but 2x plus c.
Can't you leave it as tangent power of -1 2x plus c all over 2?
Could you repeat that? I'm sorry.
Can't you make it all over 2?
That's a good question.
Like this?
Yeah.
Yeah, sure.
Okay. So what he's asking is, why isn't the plus c over 2? Right? Because the 1/2 isn't outside the entire integral. That is a great question.
Oh,
I thought about bringing that up.
You mean this?
Yep. I think that's what you're saying, right, Javi?
Yeah.
Yeah, so yeah, good question. We can write this. These say two different things, right? If we were to expand this out, we could divide both of these terms by 2, and now we have inverse tangent of 2x over 2 plus c over 2. And we can rewrite that again as the 1/2 inverse tangent of 2x plus c over 2. So how do we deal with this c and c over 2? I see you, Alfonso. 1 second, okay? I see how these are similar, but one has a c and one has a c over 2. What do? These actually are saying the same thing. We don't know what c is. It's just a constant, right? So perhaps it'd be better to say,
to just leave it out. I mean, like, leave it as tangent to the power of -1 2x over 2 plus c then. I mean, not put the plus c in the bottom, like towards the outside, I mean.
Okay. Yeah, it doesn't matter at all. It doesn't matter at all, right? Here, the only difference between these two things is this bit right here, the constant.
Oh, instead of leaving tangent to the power of -1, can't you, like, I don't know, because it doesn't look finished with the power of -1 to me.
Oh, yeah. So unfortunately, this isn't like power rule where you can like make a positive exponent by flipping it in the denominator or something. This is just notation saying this is an inverse function. If you're more comfortable with if you don't like the -1, you could call this arctan.
Is it the
And
same
then-
thing?
Yeah, arctan is the same as tangent inverse.
I'm gonna use
Arctan
that.
and
So I
tangent-
look smart on the test.
Okay.
Sorry, what'd you say, Javi?
I'm gonna try using arctan if I ever get something like this on a test. So like Miss Rose is like, whoa, he knows stuff. Plus points.
We know you know stuff.
So what Mr. C, yeah, you know a ton of stuff, Javi. Stop playing. Like you get all sorts of answers. Tangent, inverse tangent, like Mr. C was saying, is not the same thing as like x to the -2 power, right? Where you flip it and it becomes 1 over x squared. It's not the same thing. It's inverse tangent's kind of like integral derivative in that they're opposite functions, but you can't just like flip it to the bottom. It's not a negative exponent. It's just denoting that it's like a inverse.
So just to finish this off, and then I know Alfonso had a question. Either of these is fine. These are just two different constants. We don't know what the constant is, so maybe the constant was 1 here. Well, if we were to write it like this, our C would be 2, right? If our answer is the half tangent inverse of 2x plus 1, and I wrote it like this, then C would be 1. But if I wrote it like this, then C would be 2. So it really doesn't matter which one you do. Typically, we just use plus C because it's less to write.
No matter what indefinite integral you have, if the integral does not have bounds, no matter what, it's always just going to be a plus C at the end. You never have to worry about it, C being divided by anything or anything like that. So it's always just going to be plus C. That's just something you can just do automatically without thinking about it.
Okay, Alfonso, did you have a question?
No, you already answered it.
Cool. In that case, I think we're done for the day. Thanks for coming. Oops, sorry about that.
I did want to point out one more thing.
Okay.
If you actually had tangent to the negative first power, that's literally just the reciprocal, which would be cotangent. But by putting tangent to the -1, that means inverse tangent inverse. So it's just not the same thing. If we really wanted a negative exponent, and that it was actually a negative exponent, then it would just be cotangent, but it's not. It just signifies inverse tangent, which is, again, not the same as an exponent.
All right. Bye.
Peace out.
Bye.
I'm so glad Javi noticed that C not being over 2, because I was thinking about bringing it up. I wasn't sure if I wanted to.
I didn't even think of that. Good question.
Yeah.
You guys want to stop the recording?
Oh.
Oh, you stopped it.